Okay, so the transformation of stiffness matrix from local to global axis, the procedure is similar to the one that we have seen for trusses. So I'm not going to go over that, and since this is a very painstaking very painstaking formation, what you can do is you can just take a look through it and see how it's done. It's actually quite the same, similar to the thing we had done with the truss to transform the local axis into a global axis. Okay, so since this is a very painstaking process, if you'd like, you can practice it, but I don't think there's any use for deriving the final equation or deriving the final matrix, because the final product matrix is the matrix that we're going to be using to solve the problems. Okay, so we can just focus on solving problems, not the derivation. But if you'd like, you can take a look at how the derivation is done. I have put it here, and this is the final product right over here. You can see this is the final product, the general stiffness matrix in the global axis. Okay, and similar to before, here the S stands for sine theta and the C stands for cos theta. Okay, and another thing is, if you turn theta into 0 degrees, meaning when theta is going to be 0, you'll get to see that you can just place the theta is equal to 0 values in this matrix, and you're going to see that you are ending up with this matrix, the local matrix, which we have discussed before as well when we did the D2D truss. Okay, alright, so that's about it here. So let's take a look at further. Okay, now if we take a look at the local matrix and how we can easily memorize it. So this is the local matrix, you remember it from the previous lecture. So in the case of frames, what actually happens is that the axial displacement is seen very less often. And even if it's seen, for example, if this was a frame, let's say this was a frame. This is a frame. If you look at the values of shear, moment, and axial, you'll see that the axial displacement compared to the flexural and shear displacements is very, very less. So we can neglect that, right? This can be neglected. So this can be neglected. Since this can be neglected, what we can do to easily memorize this local matrix format, we can just disregard the axial stiffnesses, the axial displacements. So if we disregard the axial displacements, meaning UA is the axial displacement, and also UB is also axial displacement. Because if we consider a frame member right over here, you can see that this was UA right over here, and on the other end there was UB right over here, right, from the diagram that we had seen before. There we go. So this is XA, XB. So here this is UA, UB. The displacements are also here. Okay. So if we neglect them, if we get rid of them, what we're going to get is, let me just get rid of these. There. 1 and 4. 1 and 4. So this is the matrix that we're going to end up with. Let me take another color. So this matrix has 4 parts. This is one quadrant. This is another one. Right after that we have another one. And here is another one. Right, so we're actually getting only this parts of the matrix if we disregard the axial displacements. Okay, now to easily memorize it, you can see that this one actually matches this one. Just don't look at the signs, the negative signs or the positive signs. We're not going to be focusing on that. We're just going to focus on the components. So we have S1, S2, S2, S3. Similarly here we have S1, S2, S2, S3. Okay, so they're matching diagonally. And again, if you look at here, S1, S2, S2, S4, and these are going to match diagonally as well. You can see S1, S2, S2, S4. Okay, so you can see that. So that is how you can easily memorize it. Now another thing is that the sign conventions, the signs, right? So how do you know when to put which sign where, how to easily memorize them? So if we generalize it now, you'll see we're getting S1, S2, then we have S1, S2, right after that we have S2, S3, S2, S4, and here we have S1, S2, S1, S2, we have S2, S4, S2, S3. Okay, now if we divide it into coordinates, let's say if we divide this into coordinates, there you go, you'll see the similar picture from there to here. Now another thing we're going to do is we're going to make the third row and third column negative. If you do that, you're going to get a minus here, another minus here, another minus here, another minus here. Similarly, we're going to get the third here, the third row, a minus here, a minus here. Since there was already a minus here, if we add another minus, that is going to become positive, that's going to become a plus, and then another minus right over here. Now if you look at this, and if you look at this here, you'll see that the sign conventions are also matching. So that is how you can easily remember this matrix. Okay. Alright, so yeah, that was it for this video. Thank you very much for watching, and I hope you got to learn something new.